Wbut syllabus, the paper code for physics is BS-PH-101 and BS-PH-201, and that's for the department. So in this physics syllabus, under module 4, you have quantum physics and quantum mechanics, and I will be teaching quantum physics. This quantum physics is classified into 4 lectures. Lecture 1 will be Blackbody radiation and Planck's law. Lecture 2, Compton effect. Lecture 3 will be on de Broglie's hypothesis, and lecture 4 that will be on Heisenberg's uncertainty principle. That is lecture 1 from quantum physics constitutes Blackbody radiation and Planck's law.
Experiment about Blackbody radiation curve. But before I get into the Blackbody radiation curve, let me tell you that what is a Blackbody? A Blackbody is a body which absorbs all color of light. When I say all color of light, it means that it absorbs all wavelength of light. So if you say all wavelength of light, if I just say that what is all wavelength of light, the main source of light or electromagnetic wave, strictly speaking, it comes from the sun. And if you try to analyze the sun, you will find that if you this slide which shows the sunlight or any electromagnetic wave or light, with the x-axis is your wavelength. I can say that this x-axis, the x-axis is your wavelength. And it also have a frequency. So when you have this wavelength, so this is the increasing wavelength, this part, the left hand side, and this is the decreasing wavelength. And in this range, 10 raised to minus 4 to 10 raised to minus 6, you have the wavelength in meters, and in this range you have the visible spectrum, which I mean that it's violet to red. So when you have when you have this is violet this side and this side is red. So when you have wavelength more than red, it moves towards infrared, and more than that you have radio waves, microwaves like this. And when you have wavelength less than violet, you have ultraviolet. Less than that is X-ray and gamma. So and if you try to compare the size of the wavelength with a regular that is visible to you, you can say that, for example, under visible light, that means the wavelength of light which is visible to you right from violet to red, it is within the range of, say, for example, fingernail to in the size of bacteria. So we move to the next slide. I was talking about, we are talking about Blackbody, the definition of Blackbody. A body which absorbs all color of light. When I say all color of light, it means that basically it absorbs all wavelength of light. Okay, a range of wavelength which I just already discussed. It starts from, say, ultraviolet, gamma, X-ray to microwaves, radio waves. So when you have this spectrum of wavelength, this Blackbody, it absorbs all color of light, and then when you take this Blackbody to a given temperature, let us say a temperature T, this Blackbody can give or radiate back all the wavelength that it has absorbed. So a Blackbody can absorb all color of light or all wavelength of light, and it can radiate those wavelength which has already been absorbed can radiate back to space at a given temperature T when you take that Blackbody to a given temperature T. Now, when this experiment was going on, actually these physicists, they tried to plot this experiment value, and just on the upper panel of the slide, which has just come to your screen, the Blackbody definition has already been discussed, which is placed here. You will find when the energy of, so this Blackbody has radiated its different color of light. So different color of light means different wavelength of light. Now different wavelength of light, according to Einstein, if you just follow the equation, E is equal to hc by lambda. E is the energy, h is the Planck's constant, c is the velocity of light, and divided by wavelength lambda, and you substitute for different color of light, different value of wavelength, you will find different energy. So when a Blackbody gives out different color of light, it gives different value of energy for different wavelength. So those values of different wavelength and energy is plotted. In the y-axis you plot the energy, and in the x-axis you plot the wavelength. Now immediately you will find that there are this kind of curves, and in this slide you have 4 such curves, which means that when you have kept the black body in a temperature T1, you get such kind of curve where with the wavelength this energy increases, reaches to maximum, and then decreases with the wavelength. When you place it to temperature T2, that means when you take this black body to temperature T2, and let us say that T2 is greater than T1, it's already been designated here. So it's the same pattern you have. The energy density increases with wavelength, reaches maximum, and then decreases. Similar pattern has been observed for T3 and T4, where T4 is having the maximum temperature when the black body is kept at maximum temperature, that is T4. T3 is also black body kept at a temperature T3. It means that. So when you have a similar pattern that with wavelength the energy increases, reaches to a maximum and decreases. But one important thing is that when you keep this black body at a different temperature, you get the maximum energy density. This is the maximum part. This is the maximum part for each curve. Each curve means different black body kept at different temperature. So when you have this maximum peak, this peak actually increases with increasing temperature. Temperature means the black body kept at that temperature. So following this curve, I mean whatever I have discussed, the main points has been highlighted in the second part of the slide, which says that from the graph it has been observed that the intensity or the energy for each wavelength, so x-axis is your wavelength, this x-axis is your wavelength. So if you go down by the wavelength, you will find that for every wavelength, so if you just consider one particular wavelength, so you select one particular value of wavelength in x-axis, and you try to find out for every wavelength, for every temperature, you find out the energy density. Suppose you just take a vertical line, select a particular wavelength on the x-axis and draw this line perpendicular and such that it cuts all the curves, right? So when you just try to find out for each curve what is the value of energy density or intensity for each curve, you will find that for increase in temperature, the energy density or the energy value increases for every temperature. So the first point says intensity of radiation or energy increases for each wavelength as the temperature of the body increases. So basically this statement comes in the form of a law which we are going to discuss in the next slide. Now, if you say at any given temperature, the intensity of radiation from the body is maximum for particular wavelength, and this wavelength shift to a shorter wavelength with increasing temperature. This is a very important point. Again, coming back to this curve. So you just select any curve. So let us say the first curve, which is the first curve indicates that this curve is for the black body when it is kept at temperature T1. So you will have that for this curve with wavelength, the energy density increases, reaches maximum and then decreases. So the maximum part of the energy density, it happens for a given wavelength. Let us say this wavelength is lambda m. Again, going to the second curve, which shows that this curve is basically a black body kept at temperature T2. So similar pattern with the wavelength, the energy density increases, reaches maximum and then decreases. So for this maximum energy density, you have for a particular value of wavelength, you have a maximum energy density for the curve T2. Similarly, you have another lambda m, that means a given value of for a given value of lambda m, you have wavelength maximum, you have an energy density which is maximum. Second, again for the last curve T4, you have the maximum energy density value for a particular value of wavelength, and this wavelength, for you will find that as the temperature increases, the maximum value, so this value, this value, this value, this value decreases. That means the wavelength, maximum value of the wavelength will decrease with increasing temperature. If you just look into the T1 value, the lambda m is here, and if you just look into the T4 value, the maximum value of energy density where the wavelength is occurring is here. So this side is decreasing wavelength. So as you increase with the temperature, the lambda m or the maximum value of wavelength is decreasing when the temperature increases. So this whatever I explained you is noted in the point 2. At any given temperature, the intensity of radiation or energy density from the body is maximum for particular wavelength, and this wavelength shifts to a shorter wavelength, that means lesser wavelength, with increasing temperature. As the temperature increases, wavelength decreases. And the last point, so if you want to find out for a black body kept at a say temperature T1, and you want to find out that what is the total energy it has been given out. So when I say, again I repeat the definition of a black body can absorb all the wavelength of light. Now if you take this black body to temperature, it will give out those wavelengths, it will radiate back, right? So if you have, let us say you get this black body to temperature T1, and you want to find out, and after taking into temperature T1, it gives out different wavelength, and from the wavelength value you calculate the energy density and you get a plot like this. And now you want to calculate the total energy given by this black body at a temperature T1. What you do, you have done it in calculus in class 12. After in the differential equation part, you just take area under the curve. If you take area under the curve, immediately you will find that when the black body is kept at temperature T1, the total energy radiated by the black body can be calculated from this curve, just taking the area under the curve. Similarly for T2, similarly for T3 and T4. Now we move to the next part. So these 3 points, whatever we have discussed, is already, actually these points has been taken as laws or rules by different scientists. We move to the next slide. So whatever we discussed, we said, if you just go back to the previous slide, so it happens that for a given wavelength, for any wavelength, as we move with higher temperature, the energy density increases. So it says in black body radiation, whatever, the first point, if you recall the first point, it is actually framed in Stefan's law. In black body radiation, total energy mu per second per unit area, that means total energy or energy density, is directly proportional to the 4th power of the absolute temperature. That means energy density is proportional to T to the power of 4, and if you just bring a constant, you write U is equal to sigma T to the power 4, and the value of the constant is 5.67 10 raised to minus 8 watt per meter square per degree Kelvin to the power of 4. Now this has got a wide application. Say for example, you want to find out the temperature of the sun, right? And you calculate by somehow, you calculate the energy given by the sun. So you calculate the energy given by the sun converted per unit area, per unit time, or per second, and then you just measure the energy density. Okay, so you have the energy from the sun for per unit area, per unit time. So your value is given to you, U is given, and you divide this U by sigma. Okay, you get T to the power of 4, that means temperature to the power of 4 for the sun, and then you calculate for T, that means temperature for the sun. You get, T to the power of 4 is equal to some value, you calculate for T, you get the value of temperature of the sun. So this is a huge application. While you cannot move into the sun or you cannot approach towards the sun, but still you can measure the temperature of the sun by this law. Moving to the next law, which is already been discussed in the previous slide when I was discussing about the black body radiation curve. In the second point, that again I repeat that. So for every curve there is a maximum point of energy density. Now for this energy density occurs for a given wavelength. So for the temperature, highest temperature T4, you will have the lambda m value is minimum, and for T1, which is the least temperature here, you will have the lambda m value maximum. Lambda m stands for what? It stands for the value of wavelength where the energy density is maximum. Now moving to the next slide, and then this statement is basically comes in the form of a law. Okay, and this law is called the Wien's displacement law. It states that the product of the wavelength lambda m means the wavelength at which you get the maximum energy, corresponding to the maximum emitted radiant energy and temperature of the body remains constant. So lambda m multiplied by the temperature of that curve is equal to constant, and the value of the constant is 2.898 10 raised to minus 3 meter Kelvin. So this part, which has already been experimentally observed from a black body, is basically divided into two laws, Stefan's law and Wien's displacement law. Now, what physicists that time was trying to find out, okay, fine. You have with wavelength, if you just go back to the curve 1 second. One moment, please. Yeah. If you just go back to the curve, you will find that with the wavelength, the energy density increases, reaches maximum, decreases. With the wavelength, energy density reaches maximum, decreases. Now, physicists was trying to explain, because they know their physics is, their knowledge that time, it was some bit of thermodynamics, some bit of classical physics, say for example Newton, some bit of kinetic theory of gases. They didn't know about quantum physics that time. So whatever their knowledge they had, they tried to explain that why for a black body this curve or this kind of experimental observation they were getting. So with the wavelength, the energy density is increasing, decreasing, increasing, decreasing like this. So they tried to explain. The first one was Wien. What he did, he tried to explain this curve. This curve, I was talking about the black body radiation curve, and then he, using mathematics and his known physics, whatever physics he knew till that time, he tried to establish this, deduce this formula. This formula stands for U, which is energy density. You remember the y-axis of the plot of black body. 8 pi h is the Planck's constant, c is the velocity of light. Lambda to the power of 5, lambda stands for the wavelength. E to the power of 8, c lambda kt, k stands for the Boltzmann constant, t is the temperature, minus 1 t lambda. So he derived this formula, okay? And then after deriving this formula, he tried to put the value of wavelength and tried to get the U, energy density, from his formula, and then he tried to plot this. And he tried to compare this with the experiment curve I have shown you just now. Now, he could not fully, his curve, I mean his graph from this formula and the formula and the experimental curve which I have showed you in my last slide is basically that did not fit completely. Which portion it failed right in the lower in the higher wavelength range. So Wien's law, this formula could achieve the lower wavelength part but failed to explain the longer wavelength part. If I want to show you the this, if you are just in a better picturization, I can show you that Wien could explain this increasing part. Wien could explain this increasing part, but could not explain the decreasing part of the curve. He could explain the increasing part for all the temperatures, but failed to explain the decreasing part. Okay. Now, if you just go back to the previous slides, Rayleigh-Jeans, a group of scientists, one is Rayleigh and the Jeans, he deduced this formula, right, from his point of view, and he got this formula and he substituted the value of different wavelength and got the value of U, or energy density, and then he plotted the energy density and wavelength like the experiment, and he tried to compare. In his curve, he failed to explain this part, this lower wavelength part. The lower wavelength part he could not explain. This lower wavelength part was explained by Wien's. Lower wavelength, why I am saying lower wavelength part? If you just consider the x-axis, the wavelength, if you just go to the left, this is the wavelength value which is less. If you just go towards the right side, it is higher wavelength. So Wien, the first Wien's law, he calculated and did the derivation, established a formula, and from his formula, he can, after plotting the values, he only gets this curve, but not the decreasing part. Why? Because decreasing part you are getting for longer wavelength. Similarly, he gets the increasing part. That means for shorter wavelength he is getting, but not for the longer wavelength. That means this part he is not getting. On the other hand, Rayleigh-Jeans law, they could find, or they could establish from their formula the decreasing part. That means they are successful in getting the car for the lower wavelength. In the lower wavelength, you will find the decreasing energy density. So in the higher wavelength part, you get Rayleigh-Jeans could establish the decreasing energy density. But Rayleigh-Jeans could not explain this part. And this part occurs in which section of the wavelength? The lower section of the wavelength. So, because Rayleigh-Jeans could not or failed to explain the energy density which is increasing, and this increasing part they failed, and this increasing part is happening for lower wavelength, and we know that for lower wavelength, basically for lower wavelength, we say, if you say violet, indigo, blue, green, orange, red, which wavelength is less than violet? It is ultraviolet or gamma or X-ray, like that. So because Rayleigh-Jeans could not establish or could not prove or could not find out this part of the curve, he could only find this part, and this part is occurring at the higher wavelength, and this part which he failed to occur is in the lower wavelength. So this he failed. So this term, because he failed to explain, sometimes we say it is called ultraviolet. Planck's theory of blackbody radiation. Why Planck has to come to it with his theory? Because Rayleigh-Jeans and Wien could not explain the entire curve. So he came with a new idea. He said that you have to consider this entire blackbody as harmonic oscillator. E is equal to h nu. Why it is L? If you just go to the next slide, you will find that the energy of the oscillator will be like 0, h nu, 2h nu, 3h nu, 4h nu, like this. Point that energy, a black body is considered to made with several harmonic oscillators, and each harmonic oscillator is vibrating with a different frequency. Second, he said that these oscillators will have energy in this fashion, E is equal to h nu, 2h nu, 3. No one thought about that. So considering this fact, এই দুটো কনসিডার করার পরে Planck deduced this formula in box, which I am sure Planck's law from both science and statistics, because Planck's law deals with radiation, Planck's law deals with light. Bose-Einstein statistics deals with photons. That is why we have derived this formula, if you remember. But from this section, from quantum physics point of view, this derivation is not required. You only require this formula. Okay, you have this derivation, but from statistical mechanics part. While explaining blackbody, he was saying that blackbody is made with different harmonic oscillators, which is quantum physics. So basically, if you talk about light is dual in character. So sometimes it is behaving as a wave. Where it is behaving as a wave? Interference, diffraction, polarization. And where it is behaving as a particle, like just for example, photoelectric effect. Next lecture we will talk about Compton effect, where in the Compton effect it is light, it is an experiment of light, but basically to explain that experiment you have to consider light is a particle. And why you are considering this different? Because for Planck's, because it is from the quantum physics. Okay, what you have to study for Wbut, from the Planck's law derive Wien's law. You can see from the slides now, and this is already given in the notes. Triply you are going to get it now after the session. এই যে Planck's law, এখান থেকে আমি Wien's law তে যাব, just দুটো স্টেপ। এটা কখন Wien's law থেকে Planck's law যেতে পারবে? Wien's law কোন জায়গাটা এক্সপ্লেন করতে পেরেছিলেন? ছোট ওয়েভলেন্থ, শর্টার ওয়েভলেন্থ। তো সেই অ্যাপ্রক্সিমেশন নিয়ে অঙ্কে with the help of mathematics, Planck's law থেকে আমি Wien's law তে আসছি। এটা simple mathematics, you have to practice. It is very nothing to understand. এখানে যে অ্যাপ্রক্সিমেশনটা নেওয়া, for shorter wavelength this becomes greater than 1 and you get this. আবার from Planck's law you get Rayleigh-Jeans law. Planck's law থেকে Rayleigh-Jeans law তে আসছে। কি করে রেলাজেন্স ল কোন জায়গাটা এক্সপ্লেন করতে পেরেছিলেন? বেশি ওয়েভলেন্থের জায়গাটা, যখন এনার্জি ডেন্সিটি কমছে সেই জায়গাটা যেহেতু এক্সপ্লেন করতে পেরেছিলেন, সেই জন্য সেই জায়গাটাকে অ্যাপ্রক্সিমেশন অঙ্ক নিয়ে e to the power of h c by lambda kt is small. For that reason, if you use mathematics, you transfer this Planck's law into Rayleigh-Jeans law.
We come to the end of lecture 1, which is blackbody radiation and Planck's law. Lecture 2 will be on Compton effect. Thank you for your attention.